Thank you very much for having me here at ODSC West. Um, it's my privilege to be here. And yeah, let's just get started and start talking about LangGraph, memory, etc. I'm just going to share my screen here and we'll just get to it. Okay, so first things first, my name is Benjamin Labashian. I'm actually going to move this up here so I can see if people are commenting or anything like that. Perfect. Okay. My name is Benjamin Labashian. You can just call me Ben. I'm principal machine learning engineer at WorkHelix. We'll talk about that a little bit more in a later slide. But if you're here, then you're here to talk about stateful agents and building AI agents with memory. Today's demonstration is going to be used with LangGraph and Redis, which are tools of choice that I use when I'm thinking about building graph-based memory management for my agents. But before we get started with that, just a little bit about me. I just finished writing a second publication for O'Reilly. Can you see my screen? I hope you can. It looks like you might not be able to see it. So I'm going to try one more time. There we go. Now you should be able to see it. Perfect. And yes, I finished just recently published a managing memory for LLM agents. Talk about that a bit. I've written about AI agents before. If you're looking for the repository to code along with this workshop, you're going to want to go to LangGraph Redis workshop and under my username, which is econoben. That's what I use for lots of different things. And you can check me out at econoben.dev for my blog, etc. I actually want to start this conversation taking a step back and talking about productivity in general. We're going to get into the code in a moment, but just sort of laying the landscape here. Recently in my work Slack, someone posted an article in which this CEO of Writer AI was talking about how half of Fortune 500 executives believe that artificial intelligence is damaging their organizations. Now, my background's in data science, so when someone cites a stat like that, I'm like, I don't know the error bars on that. I don't know the margin of errors. I don't know how many people were interviewed, but as a confirmation bias sort of thing, yeah, I would believe that's sort of true. Based on my own work experience, a lot of leveraging of agents and generative AI in general is probably not being leveraged to its best ability these days in organizations. And I think part of that is that people don't really know how to roll out technology like that, which is uh, presented in generative AI. And we're going to talk a little bit about how I think about using these tools and how maybe you might use these tools in the future as well. Moving forward, a bit about me. My background is sort of to understand how to get these tools to be productive in different organizations. I work at WorkHelix. We go into enterprise organizations and try to empower employees and leadership to leverage generative AI to become more productive and use it where it is most suitable and not where it is not, so people can do what they do best, which is do the work that they're already so good at. This recent publication that I did was on managing memory for AI agents, and I was writing about a lot of the similar topics that we're talking about today. And one thing that I learned while writing this publication was basically that memory for me is the crux of the issue in when it comes to productive generative AI. What I mean by that is I think if we manage memory better, active memory, sharing memory between sessions, learning how to optimize for individuals and their backgrounds, etc., these agents will become more useful to the users that are actually trying to benefit from them. oftentimes what happens is you're working with, let's say, a Claude Code, or you're working with a GPT Codex or a Gemini, and it doesn't remember anything about you from the session before. Or if it does, it's not optimized and set up correctly. It has stale information about you, or it's just too costly when you're constantly trying to remind these sessions about you, about the context for the conversation you just had. And so what I sort of believe here is that we need to understand the architecture behind these agents, leverage them, and build better agents for the users who are utilizing them. So today, we're going to talk about two capabilities for productive AI agents. We're going to talk about memory systems and semantic caching. So the memory systems are going to be involved with LangGraph, right? That's the tool of choice that I tend to use. In there, we're going to be talking about short-term and long-term processes, so checkpoints versus stores. And then we're also going to be talking about Redis semantic caching, which I think is an awesome add-on to any agent systems for trying to reduce prices and improve efficiencies. We'll get into that in a bit. Again, if you want a breakdown of how this talk is going to go, I'm going to take my time. If we don't get to the last part, we don't get to the last part. I'm not really worried. It's in the GitHub repository. But the first two exercises is for sure we're going to get through. That's going to be about talking about LangGraph and then leveraging Redis for semantic caching. Oh, perfect. I was going to go back to show you, but again, I have it right here. If you want to follow along with me, and I suggest you do, then take a moment here, git clone this repository. It's git clone github.com, account of Ben, LangGraph Redis workshop. Then you can just cd into the folder and get started. It's the same folder that you're going to see right here next behind me. As much as I can, I try to stay within the code. So you're saying you can't see my slides? Interesting. That is interesting. Let me see if I can do something about that. Are you sure? Yeah, there you go. Interesting. I'm sorry that you couldn't see those before. You can see them now, it looks like. But I don't know what changed. So again, I'm just going to, thank you, Kate. I'll just run through this again. This was what I was talking about. This is me. This is the Riley thing. And this is the structure for the presentation. And here's where we ended up now. So you haven't missed too much here. Sorry that you weren't able to see my presentation earlier. That's what happens live. Not too worried about it. Okay, so you can git clone github.com account of then LangGraph Redis workshop.git, and then cd into LangGraph Redis workshop. You may also very much want to have Docker if you want to do the Redis example, because you're going to want to have a Docker container running Redis in the backend so that it can run that caching for you. I have a Docker Compose set up for you. If you go here, again, I like to have the code right close to us while we're talking. The Docker Compose will be here. All you need to do is follow the instructions in the slides right here, which are also in this this folder right here, the assets. So if you want my entire presentation, you can see it right here. I'm running everything in Markdown, so nothing should be super surprising for you. As I said before, I want to live right in the code with you. Want to be doing the same things that you're doing. All right, so you can follow along with me here. I'm not going to move very fast. And if we don't get to everything, the content's there. What I'm really looking for is just a shared understanding of the benefits of these tools. I have a whole write-up for you about everything here. So let's just take a step back now and talk about graph-based agent orchestration, and then we'll get into the details, etc. Okay. So what is LangGraph? I was talking about LangGraph, but I don't want to come at this, assuming that everyone knows what everyone else has. So a formal definition of LangGraph is it's a framework for building stateful agent workflows. You can have a more fancy definition there that I wrote out, but really it's just stateful agent workflows. And it is an abstraction, right? Whenever you're downloading a framework like this, that means that you're moving away from sort of that bare metal code, right? You're moving away from Python and code underneath that. But there's useful aspects of these abstractions sometimes. So for LangGraph, it helps moving from sort of function calls, because you keep going from function to function, to sort of architecture-based designing of agents. You have a repeatable abstraction where you can call out state, you can call out stores and managements, et cetera, and you don't have to focus about these other nuances. So LangGraph abstracts that work away from you, and that can be a benefit. Now, we're going to talk about a few concepts here. We're going to be talking about state graphs, check pointers, stores, nodes, edges, state, thread, and namespace. I wrote all the definitions out here for you. I don't want to read all my slides to you, but I will take a moment to talk about a few of these concepts that I think are very important. So let's first talk about the state graph. That's pretty important. Why is that important? Because this is the sort of the directive, this is the DAG that we're basically using to transform different states, different assignments of our agent using these dictionaries, right? So this is the main thing that we want to understand. And there's going to be two different concepts we're kind of adding to our state graph, this graph that is containing both our agent and our memory. The first is the check pointer. That is sort of a short-term persistence layer of a conversation. The second is a store, which is more for long-term facts and memories. So the state graph may have access to a check pointer and no store, a store and no check pointer, or the check pointer and the store. Now, the graph itself is built out of nodes and edges, which you might get from any specific graph. And the graph and the nodes and the edges are actually built through threads. The threads are these individual conversations that are happening within the graph. So you could have multiple conversations, multiple threads within the graph. And finally, you have this namespace, which is, it's hierarchical, but what really matters here is that it's a structure for organizing the stored items so that you can refer to them and think about them. Those are the important concepts that we need to know here. Really, just think about graphs, think about long-term versus short-term, nodes and edges like any other graph, and then the different threads of conversations that occur there, and you'll be great to go. Not too complicated yet. We're not getting too complicated. Okay, so in this architecture flow that we might have, you'll have a straight graph, which orchestrates the workflow, the check pointers, and the stores. We already talked about that, so I can kind of move past that. Let's talk about the check pointers for the store and talk a little bit more detail about this. And if you want to follow along, by the way, again, you can just git clone here. There are two, I'm going to take a step back and point to two different types of notebooks that I've written. So I have a solution notebook, which is all the answers. Frankly, you can start there and still go through the code and feel like you've learned everything, in my opinion, because memorizing all of these abstractions, I don't necessarily think that we need to do that here. But if you want to try to, yeah, I mean, I can. And in fact, I can probably write it out as a comment. Yes, I'm absolutely going to do that. So let's do GitHub. I mean, I can actually grab it right here and just pull it in if we want. Because that's github.com. Building. Perfect. Let me grab it and pass it to you all. I'll put it in the chat, and then we'll move back to the code. Here you go. Okay, great. Now, as you can see here, we have a solution notebook and a non-solution notebook. Basically, the difference is I've written a bunch of code for you, but then I've given you sort of to-dos about trying to build things. Frankly, what I would do if I were you is going to the solutions, reading along with me, and then later coming back and then trying to build everything yourself. It's enough to just sort of get familiar with the code, run these cells, and you'll be in a good place. I also have some setup for you here in the notebooks. So if you want to follow along with me as I'm talking about these concepts, because that's really what I think you should be doing, listening to me, but also fiddling around. I don't know about how you learn, but how I learn is just getting my hands dirty, making mistakes, trying things out, going back and forth. So you can do a back and forth between solution and building it out yourself. You can just go through the solution notebook and seeing how it works and fiddling around with it, or you can just listen to me and go back to the notebooks later, whatever floats your boat. But I use UV in this repo, and frankly, I think you should too if you're using Python. I don't think there's really an excuse anymore to use anything else. So if you don't have UV, you can install UV here. It's a package manager. You can just sync away, and you'll be good to go to start running the code. Okay, so back to the actual memory systems that are reflected in this first notebook, right? I was talking about these check pointers and these stores, which you can think of as short-term memory and long-term memory. The check pointer is the short-term memory. And in LangGraph, we have these different kinds of implementations of the check pointer. You have the in-memory saver, the Postgres saver, and the Redis saver. So the saver keyword is what you want to think of when you want to think of checkpoints, right? And it's just like you might think. The in-memory saver it's going to be an in-time saver, but it's going to be removed once you're done with your session. So every session, you've got an in-memory saver. Fine. When it's done, it's done. You can have a Postgres saver, which means you could actually use a Postgres instance or a Redis instance for a Redis saver and save scoped, thread scoped conversations to those savers. By that similar logic for long-term memory, not too complicated here, folks, for the in-memory store and the Postgres store, they are the stores of long-term memory. So you can do Postgres store or in-memory store. Notice we don't have the Redis here, but because that Redis is for caching, right? And basically the saver and the checkpoint is a cacher, right? It's caching memory. We're going to get back to that because that theme about caching, is really important to this entire conversation and to the entire concept of this talk, which is about making these agents more productive and using them intelligently. All right, let's move forward. So let's look at a snippet of code here, and we'll start at the checkpoint. And again, you can be looking at the notebook as I go along. I'll be using this presentation here, which is just presentation in my terminal. It's just a markdown file. Okay, so notice up here, we're importing in-memory saver from checkpoint memory, would make sense. We're importing a state graph. And then we're using a typed dictionary. You could do a base model using Pydantic, which is actually typically what I do. But here I just did a typed dictionary to make sure that you didn't really need anything else. And it's a named class right here with a single messages list. So it will be a list of messages, right? So that'll be what you'll be using. You initialize your in-memory saver. You pass the state that we had here, into the state graph. This is what it's going to expect. And then you can compile the check pointer at the end. Now, I've skipped some steps here. Notice here where I say add nodes and edges. We'll get to that. But basically, you start your state graph with a state, which is it's got a state and it's expecting messages. This can be anything you want, really, that is expected from your users being passed into the state. Then you can compile the check pointer for short-term caching of those things. And what do we have here? So once we've compiled our graph into app, you can see that each thread is invoked, that's literally invoked with what we expected, which was what? A messages key and as a value, a list of text. So we can pass those in. And then what we can do is give the thread just an ID. So we say, well, this is going to be the conversation one. We passed all the conversation to this thread and we can invoke it. So again, this is just walking through some of the code for LangGraph and the check pointer as we're going through. Okay, now let's compare that with our long-term memory implementation, right? Very similar to what we had before, but here we have this in-memory store. And notice the difference here. So we have the in-memory store that we initialize, and then we have store.put, whereas before we didn't have anything like that. We didn't have store.put. And we're storing a fact into this namespace. We mentioned namespace before. Namespace is a way for us to reference something. So in this case, it's going to be the namespace user facts related to user underscore 123, right? So there's some user that we named here. It's going to go under user facts. You might have user facts, user 432, et cetera, et cetera. You might also have a namespace that has nothing to do with user facts that are for long-term memory. But in this case, namespace. And then we have a key relating to that information. In this case, it's their occupation. And then we have a value. And the value is a fact, which is software engineer. We believe that they're a software engineer with a confidence of 0.95. Easy so far. So now this is placed into our memory store. It's a put. Basically, it's just an API call that says, it's an abstraction away that says, here, I'm sending you this information. Like you can think of this as just a dictionary that you're sending to a database. And you're absolutely right to think like that, right? Now, LangChain, LangGraph, they abstract away some of this work, but in exchange, we can just get this stuff done because we know what we want to do in a repeatable fashion. After we've sent the data, then we can search for that data. So what if we wanted to search user facts for user 123, but we want to search it, this is the interesting part, using natural language? Well, we can do that. In this example, we have an LLM attached to it, so just assume that that's happening. We can say, well, what does the user do professionally? It would pull this fact out, and it would give us software engineer. If we wanted the metadata, we say, how confident are we in that? 95%. And we can get it just through parsing through this list. All right, so that's our long-term memory implementation and our short-term memory implementation. But let's take a step back here and just think about a through line as we're going through this work, right? When I was writing my publication on managing memory for AI agents, I came across this sort of way that people tend to think about it, right? Which is there's semantic memory, episodic memory, and procedural memory. And one thing that happened while I was doing the research was I was thinking, well, why are we choosing to think about memory in terms of human sort of concept of memory? Like, why does memory have to be necessarily human? Couldn't it be something else? Well, it turns out that there's some really good reasoning I got for this, and I sort of agreed with it, which is we have decades worth of psychology research. And that may be good or bad research depending on the study. But what is sort of incontrovertible is that one takeaway from this research is that human memory is really fallible. And so is agent memory. Agent memory is very fallible. And so under those constraints of fallible memory, how can we build software to work around these notions of certain types of facts or conversations or behaviors and programmatically work around them, knowing that this kind of work is not deterministic, but non-deterministic. And in that way, these three categories really help sort of create a framework around them. They're an abstraction. They're not perfect, but they're helpful. So I'm going to start from the bottom here. One kind of memory we might think about is patterns, instructions, learned behaviors, habits. So these are like if I went and I copied to-dos from like the LangGraph doc website, and I pasted it into ChatGPT and I said, follow these instructions, right? That's a procedural memory. A semantic memory, now I'm going to jump to the top, those are facts, right? That's really simple. What is, what isn't? Tell me about X user. Tell me Y thing. That's semantic memory. And then there's episodic memory, and those you might think of as conversations, right? That might be the short-term memory that we were talking about before. And so we're talking about these short-term and long-term memory implementations. And while we're doing that, maybe ask yourself, as an engineer, as you're building these things out, will this be an episodic memory? Will this rely on procedural memory? Or will this rely on semantic memory? What kind of memory will my user require? Will they require some combination of the three? That's something to think about as we're moving forward. So I wanted to take a moment to step away, talk about, wait, what are we doing here? Why does this matter? Okay, now let's get back to memory implementation patterns, now that we have a little bit of theory behind us, as well as knowledge about short-term and long-term memory. So there's this sort of three-node architecture that people can use when we're using agents. I'm just going to take a sip of water here. Okay, so the first is this retrieve process, and that makes a lot of sense, right? That's just retrieving long-term memories. Can we retrieve memories before we do anything else? Then there's the process. The process generates a response using memories. And finally, there's a store, which is, did we get any information? Let's take it and retain it. So let's walk through this a little bit more deeply here. So you have the retrieve memory node, which goes through, grabs the recent content, and then runs a search, right? A query. And it basically says, go through the last message. Do we have memories relative to the last message that we stored relevant to what we were talking about? Everything's going haywire here. Let me try again. Next, we have this process node, right? Let's generate a response given the last message we had and the memories that we've retained, if there are any useful memories, and provide a useful insight back to the user. So we get the we format the memories, we add them with the messages that we have, we invoke an LLM response, so we pass them through to the LLM, and then we get a return to the user based on the memories, which makes a lot of sense, right? Someone asks you a question and they say, tell me about the Redis document store. And you could say, I don't know anything about the Redis document store. I'm going to have to do that. Or you could say, actually, I know they're a machine learning engineer. They will probably be more interested in this kind of stuff. Let's add that information while I'm looking up information. That's kind of relevant. And that's what, when you're talking to something like ChatGPT in a very abstracted way, what might happen. And finally, we can store memories. Maybe we provided information to the user that we think is very important. Maybe they provided us something in the message that when they sent to us. So what we can do is we can extract facts. And right now we've just got this abstraction that we're calling extract facts. We don't need to look into that yet. We're going to look into that more in a bit. And we're going to take those facts and we're just going to send little API calls to either our local store or to our Postgres or wherever we're retaining long-term memories. And as you can already see, conceptually, this kind of makes sense, but it starts to get, the word I would use is large when it comes to, there's a lot of things that you could store, right? The database might start to get pretty big. You can imagine the kind of database that OpenAI has, for instance. So one thing that you want to start thinking about as you get more advanced, and we're not going to entirely talk about that today, but it's important to realize is what kinds of facts are you going to retain and what types of facts are you going to not retain? Are you going to ever compress those facts to make them smaller? Are you going to discard facts over time as they become less relevant? These are the types of things that start to come to mind as we start building out more professional, more rigorous agents for our users. Okay, so I remember at this point that I have skipped an important detail. Remember back here when I said add node and edges right here? Well, I said we'll get to that. Now we're getting to that. When we start our state graph, you start with some sort of memory. Let's say that. Let's say we started with some sort of memory. We want to then retrieve memory, which we're going to call, we're going to give it a key and a value. The node is going to have a key and a value. The graph is going to have this key value pair for retrieve memory, which we're just going to call retrieve memory. And it is this function that we've just built right here, retrieve memory node. Then we want to process. And in this case, we're going to call it process. We could call it foo. We could call it Cheryl. Right now, we're calling it process because it makes most sense. Store memory. Now we can add a store memory to it, which says store memory. But how is the graph supposed to know what we should do in each phase, right? In that case, what we're going to be doing here is we're actually going to start creating a real DAG, a directed acyclical graph, right? In this case, we're going to start which is an actual keyword that we can download or we can import, I should say, from LangGraph. Then we're going to end here, which is also the end. And in the middle, we're going to determine our flow. So we're going to connect node to node, right? And how do we do that? Well, with an edge. So that's how graphs work. So this abstraction is kind of useful because we already know kind of how graphs tend to be, which is node, node, edge. Well, then node start to node retrieve memory, then create a new edge between node retrieve memory to node process. That's a new edge. And create a new edge process to node store memory. That's going to be a new edge. And finally, node, we're going to do node store memory edge to node end. And that's how our process is going to work with our simple LangGraph agent right here. So we're going to do all of that. And once we've done that, we can compile. We're going to compile. We're going to say, okay, graph is created. Now, build it out. Because when we're doing the things above there, it hasn't really been compiled yet. It's just saying here are some directions we want to do. Maybe we're gonna change it. We're gonna whatever. Compile is only when it's really saved. And if you notice, maybe anyone's paying attention here, we actually have our check pointer and a store here. So in this case, we're going to retain conversation history in a thread and a store for long-term memory, which makes a lot of sense because we're going to try to access memory. And so this could be a full agent that we're running and deploying in production. Okay, let's talk about threads a little bit. You can do conversation isolation, basically. I'm going to kind of skim over this because I don't think it's the most important part. But you could have multiple threads, right? So you could say, I have a configuration for isolating one thread, which we're calling conversation alpha. You can automate this and make this a factory. So it just names them as you go and does a random UUID. But you could add these configs and have another one here. So it could be the same user, but a different thread. So they might have had multiple conversations, which is very useful. You want to track a user over time. And then remember, when we had that memory, or we had that messages and list class before. That's what we're expecting. This is the same class. And so then you can pass this thread here to invoke this isolated memory, or you could even pass them both. Okay. So at this point, we've gone through, when I was initially building this this talk, I was thinking like, hey, we could take a bunch of minutes and just go through things. I would say here, I'm just going to run through some examples of how this works. And then we're going to just continue and go on to the Redis example here. So I already have UV in it. I already have my virtual environment, which is containing all of my packages, and I've synced everything up. Okay, so in this case, I can use, let's say, an OpenAI or an Anthropic API key. You can look to this environment example here to create your own. All you would have to do is copy this, create your own environment right here. I'm not going to actually press that button because that's where my actual keys are. And you can copy the API keys here. You can name whichever Claude you want. This one says 3.3.5, but I'm using 4.5. We'll get to that later. That's fine. Same thing with OpenAI. If you wanted to do something with OpenAI, you could have used that as well. And there are a bunch of different functionalities that you can do. A Redis URL, all that's running in my Docker container right here, which is just it's just running Redis in the background. I have more instructions about that in the repo. Right now, we're going to just move forward and talk about some of these things we've been going over earlier. So I'm using an Anthropic key, I believe, so I can just press go, and it checked for my Anthropic key. I bet if I just didn't run anything, then, or let's say I ran OpenAI key instead, it would error out. So I tried to be very vigorous or rigorous when I was writing this out. So we've got a chat Anthropic extension from LangChain that basically says, hey, we're going to call Anthropic for you. This is just an abstraction. It's literally an API call. It's nothing really that technical. So, you don't have to rely on LangChain for this part. You could just do this yourself and it wouldn't be a big deal. Same thing with OpenAI, but for this point, we're just going to use the LLM object here because it can be helpful below. So we're using that. And now we're going to just go over this short-term memory check pointer, right? So we have this state right here, which is just a type dictionary in which we have our messages list. And the list has this little add messages function right here. And this merges two lists of messages, right? So basically what will happen here is the messages will all become one one list. And we get add messages from this LangGraph messages thing here. So as more memories get added, they're just getting truncated together. These are little abstractions, not huge time savers. You could do this yourself if you wanted to. We've got our in-memory saver, right? It's a saver, which means that it's a check pointer. It's not a long storage, right? It's not going to be something in Postgres or anything like that. And state, right? So we're passing our state, which is, again, this right here, what is being expected to be passed through our state graph. So we can run through and we can define a little chatbot. And we can say, okay, here's a little chatbot, define a little chatbot, have a little node. There's going to be one node, and the node is just going to be chatbot. And look here, all I had to do was just say, here's my little function. I'm going to invoke LLM, which is just going to be an API call to whichever LLM I'm using, in this case, Anthropic. I've got my little chatbot right here. I'm going to pass it as a node. Well, what's the edge of a single node? Well, it's just going to be between start and end, which, again, we imported from up here in LangGraph, right? So we can still have a single node, and it'll work because they give us start and end nodes to work with, and are just a little check pointer right here. So we create this little chatbot with memory, and all we can do, or all we have to do here, is we can create a little thread, and we could say, hi, my name is Alice, but just in case you all don't believe me that this is really working, we could say, I'm Ben. I do software engineering, sure, at WorkHelix. That's fine. And I can even take this out. So there we go. It's running. And then I'm going to get a response. The response isn't there yet. We can't see it. So let's get the response information. We're going to get the last message from this list response that came from our invoke, which is that's an API call to Anthropic, and get the content there. So let's do that. Hi, Ben. Nice to meet you. WorkHelix. That sounds interesting. What kind of work do you do there? Software engineering. Well, I could run back and talk to it again. The problem is it's not going to really remember what I said. Oh, but it might, because I have my check pointer. Let's check. What do we think is going to happen? What's my name? So we're just going to say, here's a message to them. We're going to invoke, and we're going to get response to. And we're going to keep the config right there in our invoke. What's going to happen? Let's check it out. Will it remember what? My name is Ben. Well, it couldn't possibly have known that unless it was using the check pointer. So it does retain short-term memory, right? So this is a way to keep a short-term memory going. And then if I wanted to do response 3, if I was being really fancy here, I love to live code, it puts me on the spot and say, where do I work? Let's actually try a question that that it wouldn't know. When was I born? Right? Let's throw that in and see what it says. We're sending an API call, and I don't know when you were born. You haven't told me that information yet. Perfect. That's true. I haven't. Our experiment worked. We're happy. Let's move forward. Our in-memory store. In this case, we're not going to put this in like a Postgres or a Reddit or a Redis or anything. In fact, Redis doesn't have a store for this. We've got a state with memory, and we've got messages in our class, but we also have our memories, right? So we're going to retrieve memory. I want to keep going a little faster because I want to get to Redis as well, the Redis example, but this is fun, so let's keep going. Retrieve relevant memories from the store based on the user's message, right? So we've got our last message, our query, which just says use the last message, or if it doesn't matter. Basically, we're going to go here. We're going to search with our query. We're going to get extract memory content. So this is a chatbot with memory. We're going to join our memories together. We're going to give a system message that says, here's what you know about blah. In this case, me, whatever. And then we're going to invoke these together. It's going to send the system message that tells the system, hey, you know this about the people, and here's the message that you're going to get. So there's a difference between the long-term memories, which are going in the system message, and the conversation history that are going in the messages, right? Okay, so pass that through. And then if we want to, we can store the message. We'll do that in a second. This is what it will start to look like. So we have our state with memory, which again is right up here. I know I'm speaking kind of fast, but we have our messages and our memories. I would happily talk more about this in the future. But for now, this is what we got. So let's see, retrieve memory. retrieve memory. We can call this whatever we want. These are just we're establishing our nodes, and then we're saying this is the order in which you do things. We retrieve the memory, we chatbot with memory, we store the memory, and then we compile. Let's run this, and the long-term memory is saved. Now, there's something I skipped over here, which is the store memory function, which I think is really fun and an interesting concept, and so I want to talk about it with you all today. The store memory function that we're building out here is we're saying, get the last user message, and if it has information, then I want to retain certain facts. But let's just take a conceptual step back here. How are we determining what is a fact to save? Remember, I talked about a little bit about that before. Where are we getting that information? Well, in this function, all we're doing is we're saying if we contain anything like my name is, I am, I work, I love, I like, I enjoy, I prefer, we're going to take that information as a heuristic and we're going to store that information as a fact. And that's what's happening here. But of course, that's pretty shallow, right? Because I don't always use those words to determine something, and that doesn't necessarily mean that it's a useful fact to keep. So what do agents do in the real world? Well, they do something a bit fancier than what I'm about to show you, which is what if we could extract facts themselves with an LLM or with an NER or something like that? You absolutely could do that. So in this case, here's how it would work. You would try to retrieve store memories via this prompt that says you're a fact extraction system, extract memorable facts about the user from their message, return only a JSON, etc. Return that information. So here's some examples. My name is Alice, username is Alice. I love Python, user loves Python, etc. Could we do something like that? Well, in fact, we can. If we do LLM invoke, have a system message and a human message, call the LLM with an extraction prompt, parse the JSON, which, gosh, we hope that it sends us. What if it doesn't send us a JSON? That happens all the time in production, and it can be a nightmare. We try to extract the facts out, and then we return them as a JSON, which is basically just a dictionary with facts as the key and a list of information as a list. All right. So then what we would do is we take that information and we would run this extract facts with LLM, extract it, store each fact with its own unique UUID, and there you go. You're running through. And instead, we would have this graph right here, which we can compile. So what would that look like between the two things? So first, we can run a test message. I'm going to actually split these up because I love to live dangerously and run this stuff live. So we've got this test message. I'm a software engineer at Google. I love hiking on the weekends. My favorite food is sushi. Great. Let's see what a direct extraction would look like. So the direct extraction is the first one we built. That's with those heuristics we were using. I love, I like, etc. What does that look like? Let's try to extract facts with LLMs there. So if we run that, we got 3 facts extracted. But that's because, what did I say? I'm a software engineer. I love hiking on weekends, and my favorite food is blah, right? I'm pretty sure most of those facts, if we look in here, I like, I love, I work, right? That's our extraction. So if we change these to something else, that might have not happened. Okay, let's do, so we've got that. Now we've got the full agent with LLM extraction. Let's see what happens there. If we print that with an LLM, it's going to take longer. So we stored certain information. We've got the information here. We've extracted it out. There are pros and cons to this, right? If you had a simple heuristic, it wouldn't take so much. So it would take money or it would take less money and less time to produce. But on the converse, you're going to probably get fewer facts. So people are usually using some sort of small LLM to extract those types of things. Okay, let's move forward with the presentation because I want to get to the Redis part. And I know we're going through pretty, not going through the entire presentation yet. I knew we wouldn't get to the last part. So let's go to the Redis semantic caching theory part, and then quickly go through that to get to the meat of this presentation. Okay. So first, why are we bringing Redis into this? What does Redis have to do this? Well, Redis is caching, right? And if you can think of one thing, you can think of Redis as caching. And there are benefits to caching certain responses to working with LLMs. I talk a little bit here about theory. I don't necessarily think we need to talk about that here. So if you want to just go through the slideshow, you can do that. I'm going to skip that. But what I will say is there's a difference between traditional caching, which is you can create a hash of certain query strings and exactly get those hashes back, or check hashes if they happen. So if someone says, what is Python? And does that equal what is Python, but without an or a question mark, they'll have different hashes. Caching in the semantic sense, which is what Redis is doing, is what if you have a similar question being asked of an LLM? Do you want to always call it? Well, that can be expensive. Now, if you're an internal agent for an enterprise and you've got thousands of people, literally Amazon, the company, has like 1 million workers, right? What if they're all using an internal Amazon Q database and they all are querying similar questions or whatever? We don't want to do that. So if we have a cached query, we can return cached answers and reduce the cost of compute and increase the rapidity with which people receive their answers. So if someone says, what is Python? Or tell me about Python, or explain Python, they're very similar questions. And we might be able to get an answer back quicker and not have to use the same LLM to calculate the answer 3 different times. So there's different variations to the same kinds of questions. And I've basically explained what that is there. So Redis data structures tend to be store a query and have a response map. You've got hashes, which store query metadata, and you've got sorted sets. Sorted sets maintain things like how long to retain cached object. Maybe the question that's being asked is relevant, but it is old and we want to get a new update about, say, Python. Maybe Python 3.14 came out and people will need the update, right? So you can use Redis as a means of retaining this information and pulling it up faster. Here's a bit of a diagram here. You're going to want to get a bigger screen for this. All you need to know here is that this is kind of the structure with which Redis queries occur. Not a big deal. We're gonna go through that. And then we have different kinds of similarities. I'd love to go over the math with you a bit here, but I've got the slides for you. You can use different kinds of similarities to determine if a question is similar to something that you've already retained in a semantic cache. So you can use something like Jacquard similarity or cosine similarity, which is the one that people tend to use with embeddings. As a quick note here, it's not always the same to use. Like, you shouldn't just think cosine similarity, right? Based on the embeddings being used, based on what the distance functions were being used in the algorithm, you're actually going to want to look those up, because dot product might be the right way to do things. You don't actually know. People kind of just use cosine similarity as a heuristic and think it's always going to be the best similarity metric, but that's just simply not the case. And then you can, do a lot of things about caching versus precision and recall, but I don't have time for that here. So I'm going to just move ahead here and talk about actually caching these calls. Okay. First thing we're going to do here is we might have some sort of Redis client, right? So there's this Redis client right here, and you can establish a time to live. In this case, 3,600 seconds, which could be an hour. And then a similarity threshold. You might say, okay, as long as it's close enough by 0.9 in Jacquard similarity, you can pull it up. We can even implement Jacquard similarity, which is pretty straightforward here, which is just the set of words in string 1, set of words in string 2, and then the union between them, and then just get the length of both of those and then divide each other by them. Okay. More importantly is the Redis caching, right? So you can have a get query, right, which basically searches the queries within a given cache and say, in a given cache, for key in cache keys, return the Jacquard similarity for those cache keys And if the similarity is greater than or equal to the threshold, then you retrieve back a cache hit. Otherwise, you can set the response into the Redis cache right here, which is setX. And then in the future, that will be applied when we're trying to calculate the similarity scores. Let's look at an example here. I'm going to go straight into the notebook. I know that we have a few minutes left. And we're going to go through. And we see here we're already got Redis connected. And we already have those similarity scores like I was talking about before. We've got these get calls right here and calculating the thresholds. And we can even catch if there are misses. We can set if there's something that hasn't been put into the cache. Perfect. And let's build a cached agent, right? So now here we have the state. And in this case, we have a cached state. So we have our messages, we have a cached state, and we even calculate latency, how fast it took to get a message returned. So we can gather our messages as before. We gathered their messages. We can try to get a cached response. If we get a cached response, calculate the time and return the information. Otherwise, call the LLM, calculate the time it took to calculate the response, and return. Pretty straightforward. So in the state, what we do is we pass in the state right here, the cache state for our object. In this case, we're caching or we're keeping messages, caches, and latency. Then we create that node, an edge where it's just a cache chatbot, and see what happens. We run this. If we run, let's start down here. Let's run this first one. Invoke what is LangGraph. Let's see if there's a cache miss. Latency. LangGraph is a framework developed by LangChain. Now let's call that same query again. 0.02 seconds. Sorry, 0.002 seconds. That's 2,000th of a second. So the first query took 8 seconds. The second query, which is what is LangGraph, took 0.002 seconds. And we got the answer back. This is a really great illustration of why caching these kinds of LLM responses can actually be incredibly helpful. Imagine if OpenAI or Anthropic with Claude were caching all of its responses and then could just pass similar responses back to the users. Now, it might not be that easy, but imagine how much less compute might occur, right? Let's look at the speed up here. 5,317 times faster by using a cache response, which is just looking at a similarity score. Let's test also our semantic matches. What if I did tell me about LangGraph? Is that going to be as fast? I'm betting it's not. I bet based on the low threshold that we had or the high threshold that we had, yep, it took 9 seconds. So we cached, it was not cached, it was false. And then we can measure some cost savings. So if we ran this, what is LangGraph? True, 0.03 seconds. Tell me about LangGraph, 0.03 seconds, because we already ran that. Now let's calculate some savings. And then the last 5 minutes I'll leave to questions. The rest of the presentation is very similar to what we're talking about here. So we've got 5 hits, 3 misses, a total of 8 queries, or a total of 8, and a hit rate of 62%. Okay, thank you for Justin for the README information. I'll update those. That might have been I've had several different iterations of this talk, and I don't know what happened to those links, so I'll fix those. But we have a cached hit rate of 10.13 seconds, total latency of 10 seconds, time saved 1.3%, savings 62%. Without cache, it would have cost this. With cache, it cost this. Therefore, we saved 62%. So already here, based on using the LLM, we can see that not only is it beneficial in a time sense, but in just some basic assumptions about how much it costs per request, we're getting information about how much we're saving by caching our calls. So I know I'm towards the end of my talk here. And I appreciate you all sticking with me through the technical difficulties of those slides. But what I think is important to retain from this presentation here are the fact that you're learning about long-term versus short-term caching, the fact or calls with invoking short-term savers and long-term states, and then also keeping information about caching and how caching can improve the speed and cost savings using any sort of agent calls you might have. I'm going to take these last 3 minutes because I've been talking a lot and talking very quickly to answer other questions that people might have. I will update the README. There's some other things I need to do to update for the GitHub here. But yeah, you got the main thrust of the conversation here. I hope you were going through some of these questions and in the notebooks. The rest of the presentation was basically me going through memory and caching, talking about implementations, and talking about monitoring these types of things in your organization. But at the end of the day, look, if you're learning about memory, I would go to check out the LangChain the LangChain documentation, and specifically the LangGraph documentation. I don't use LangChain as much as I use LangGraph. The memory guide for things like checkpointers and stores, and also Redis with their semantic caching and their LangCache, which is pretty special. And yeah, and let me know if you have any questions. Feel free to reach out to me. You know, I'm at EconoBen, and you can also check out my blog at econoben.dev. Don't use a specific fax break caches very easily, or is there a specific and easy good way to deal with that without invalidating the cache? Yes, there is a very specific way that you can handle that. Very good question. You can have user-specific caches, right? So, you know, the way we built it for this simple example is that we built a cache for a universal cache, but that's not how I would build. It depends on what you're using the agent for, but that's not how I would build a cache in, say, like an enterprise. In an enterprise, I might have, say, a universal cache, and then maybe even a user-specific cache or a team-specific cache. And that would make things a lot easier. I would experiment with my user base, really know who your users are. For something universal, maybe say, hey, you're using an LLM for searching a document store, you in like LangChain docs or something. Maybe you don't need user-specific facts. You just need facts about the documentation. But if you're going to need to know things about specific users, you might have a user-specific cache. Great question. It's very cheap to have as cache. Just throw another cache, throw another Redis cache, another. All right. Thank you so much.